student of mine, Zhongwan Ying. I got paper credits. And the first two are this one's my PhD students, and that's my collaborator from Donghai University. Today I want to talk about large-scale estimation of forest about ground biomass in Taiwan. And forests occupy about 30% of the world. It's not the largest vegetation type. The largest vegetation type, as you can see, actually are dry lands. But they store the majority of carbon and the biomass of the terrestrial environment. So it's important to estimate. It's crucial to estimate biomass for the biosphere. And then arguably probably the only way to do that is using remote sensing. And then using remote sensing conventionally, the people do the remote sensing carbon estimation. First of all, they classify the vegetation. So they have different types of vegetation. They estimate the mean value of each kind of vegetation type, and they do the extrapolation to estimate. But the thing is, when you do that, you kind of assume the landscape, each vegetation is homogeneous within its vegetation type. And here's an example in Amazon. And if you use the conventional way, the land cover looks like this. However, if you use high-resolution remote sensing with advanced technology and algorithm, that's what you actually see. So that is a big issue for if you just use IPCC Tier 1 approach to estimate the biomass of the region. So today I want to introduce a new approach, and then we are working on a report on using this approach to map the biomass of tropical and subtropical ecosystems. And we coined the Ecosystem Complexity Observation by Integrated Remote Sensing System, ECO-IRS. And then it basically includes several components, including, first of all, you have a satellite images. This is example using Landsat. So you have a Landsat images. You do some atmosphere correction to remove molecule scattering and aerosol scattering. And then you do the cloud cover removal, because in optical remote sensing, you can actually use this kind of data. On the other hand, you have a big library of some M members. And then the M members are basic component to composite a pixel in the nature area. So the three major M members are green vegetation, litter. Litter is like something you cannot do the photosynthetic vegetation. Something is vegetation, but they cannot do the photosynthesis. So it's like tree bark, or dry grass. And then soil and rock. So we measure this using a handheld portable spectrum radiometer, and then we resize it to, in this example, it's a Landsat images. And then we do something called auto-MCU. It's kind of spectrum mixture analysis. And for each pixel, we're using some Monte Carlo mixing to estimate its mean value and uncertainty. So ECO-IRS actually integrate in three major components. Is the atmosphere correction using Acorn. It's invented by JPL and Caltech. And then the other one is the cloudy shadow. So remove these noises from the images. And then codes are written by myself. And the auto-MCU is a kind of mixture analysis model. It's invented by Stanford University and Carnegie Institution. So the first part is the atmosphere correction. It's important for pre-processing an image. So here's a hyperspectral average image. If without remove like water, aerosol, and molecule scattering, it looks like that. After atmosphere correction, you look at actually both of them out of the same image. So the second one is called the shadow cloud removal. So this is the original image. This is an important step in when doing tropical research, because you see clouds and shadow everywhere, especially in Taiwan. And then you remove the cloud and shadow. And the third one is called auto-MCU. Auto-MCU is an algorithm. You basically collect a bunch of PV, MPV, and the MPV is vegetation, but they don't have green leaves, or the bare soil. Then you resample to different kind of spectrum with atmospherically corrected images. You do the mixture analysis So the output will be the fractional cover of PV, NPV, and soil. So the first two I just introduced. The third one, so we collect a bunch of N members. So we go to, in the 2010, we have field campaign for the whole year. In 2010, so we have 7 sites across region, across elevation. So because I'm from a very small lab, so everybody got to go to the field. So everything here, 2 legs, are my lab member, including, no, not including this bird. But so we collect a lot of different kind of data. So we have a lot of data, so we can do a spectrometric analysis. So EcoIRS is an automatic system, can be executed now, can be executed in Windows XP 64-bit and Linux. The codes are written in IDL. Now EcoIRS is ready to process Landsat, MODIS, AVERS, and Hyperion data. We don't try to use them for some high spatial resolution data, such as QuickBird, Iconos, or GeoEye, or other kind, or Spot, because they only have 4 bands. So at least you need to 6-7 bands to do a good mixing. And EcoIRS, now we are working on Ali and Aster, mainly because there are not too many good images for Taiwan. We got to use as many different kind of images as possible. So what's that actually to do with biomass? So one output is fractional cover. So actually so if the output will be NPV, PV, and soil. I just find that actually the color is different from the screen and my computer. So actually, so that should be, so if you have 3 N members, you can put, presumably should be RGB. So if you loaded 3 into the RGB bands, you should see something like this. So we have the fractional cover, PV fractional cover. We link them with some field biomass data. And then 3 of them actually is from the forest prop they just introduced in the first talk. So we combined 20 of them. And I got some help from my students and my colleagues at the Taiwan Forestry Research Institute to help me to sort out which kind of data are useful for this study. So we narrowed down to 8, but in this week we have 3 additional plots for this area. And we link the PV green vegetation with the above ground biomass density. Look at the unit, it's per hectare, ng biomass per hectare. So you multiply by 0.5, it's about carbon. So you have this, so you can measure the biomass of the forest area of Taiwan. And the strength of this map, all the category, each pixel, this is a kind of continuous data, numerical data. So you don't really need to have the vegetation type. And you don't need to really worry about the vegetation. You don't need to really worry about the classification accuracy of the vegetation types. So we estimate the forest biomass density is about 160 megagram per hectare. So total forest carbon storage for Taiwan, here what I say forest is about 40% of vegetation cover. So they will be like hundreds of definitions about forest. Some of them 20-30%, some of them 70%. But for this study, we used about 40%. So the total forest carbon storage for the entire Taiwan is about 141 teragram, and 1 teragram is it's a lot anyway. So for EcoIRS, we can estimate some outputs. It's green vegetation fractional cover, NPV, non-photosynthetic active vegetation cover, and the soil. So for the PV, so PV per se, fractional cover is actually very close to something called APAR, assorted photosynthetic active radiation. So if you multiply APAR by this is called light use efficiency. So use some model called Carnegie M Stanford approach, CASA model. It's a NASA model. So we can measure So the fractional cover actually is equivalent to F part. So you have solar radiation, you have maximum light use efficiency, water and temperature. You can measure the MPP. And the other one, we just use similar model to estimate the biomass and the cover over some dry land area in Pinyon juniper of North America. Recently, we just wrote a paper about using MPV, because MPV related to tree die-off. It's probably not that common in Taiwan, but in a lot of countries like North America, like in Europe, like in Australia, you can see a lot of trees die due to early drought this century. So this is kind of tree called aspen. This is the most widely distributed tree in North America. And they are actually the largest tree organism in the world. So actually, you look at all these small trees, they are actually called suckers. They all actually, the whole group is one unit. It's the largest tree. It's the largest tree in the world. So you have biomass lost. And then because you have MPV cover, we can actually estimate how much live biomass losses due to like tropical hurricanes. And this is another MODIS data. We use MODIS time series PV fraction to estimate the litter fall of some forests. And the most important is we are actually submitting a proposal to National Taiwan University. It's a five-year proposal. We try to integrate eco-IRS, the system, into something we coined it. It's like ecosystem complexity observation for network of terrestrial unit, eco-NTU. It's similar to the mega project in the United States, and as is the NEON project. So we have actually 5 areas with all the frost tower, and the water quality measurement, nitrogen measurement, carbon emissions with hyperspectrum data. So we consistently measure data from these 5 sites. So this is the just initial project about how to use advanced algorithm to estimate useful information for ecological study. So that's it. Thank you.
So thank you very much. So let's have a time for question and answer.
Yeah, you mentioned about the tree dies. Is that a way that we could rescue the